Hi everyone, welcome to the class guys. Please confirm once that am I audible to you or not. Shillong, Tamelong, Itanagar. Guys, can you hear me? Okay. Hi everyone. Okay. In the previous class, hi Tamelong. Okay, so in the previous class, we have done the electrochemistry. Today we have to start with the solid states. Okay. Solid states. See, gaseous state we have already studied in the class 11th chapter. Okay, and the next state is what? Solid states, that what we have to discuss here in the class 12 section. So, before starting with the solid states, let's have certain properties of the solids. Okay, some general properties of the solids. Let's have a quick introduction to the solids, and after that, we will have an imaginary world. Okay, and yes, guys, one more important thing. Please make sure that you will be connected with me while studying this chapter. See, this is very interesting chapter. But yes, if you are not connected to me in this chapter, then this will be very difficult. Okay, difficult as in obviously that you will be able to solve the questions, because there is very limited concepts. Okay, very limited formulas actually. Okay, if you even learn all those formulas, you would be able to solve the questions. But the point is, if you talk about the concepts, so concepts has no limit in this chapter. Okay, so please make sure that we will have the proper idea of the concept. Okay, so let's start with the solid states. And yes, few of its important properties, like if you talk about the general properties of the solids, they are incompressible, they have definite shape and definite volume, their particles do not move, they actually vibrates on their own positions. Okay, so these are the general properties of the solids. Okay, so let's begin with these properties, and then we will start with that section. Okay, so you can copy this part with me. You can start copying that. Properties of solids. First, they have definite shape and definite volume. Next, the intermolecular distance are short. the intermolecular forces are strong. They are incompressible and rigid. Their constituent particle like atoms, ions or molecules have fixed positions. And can oscillate about their mean position. Okay, please copy it. Intermolecular forces means the attractive force which is present between the particles. The attractive force which is present between the particles. Please copy and then confirm. For example, covalent forces, hydrogen bonding, van der Waals forces, dipole-dipole forces, London forces. Got it now? Copied now? Okay. Crystalline and amorphous solid. Okay, so I am creating a difference table. Okay, and we will discuss that how these two are different from each other one by one. Crystalline, and here we have the amorphous. Okay, so you have to create this difference table. Now, first point, they have definite characteristic geometrical shape. geometrical shape, whereas they are having the irregular shape. Okay. Number 2, melt at sharp and characteristic temperature, whereas in this case gradually soften over a range of temperature. Yes, I am discussing. Wow. Is there anyone who is still outside the class? Shillong? Okay, good. The second point says that melt at the sharp and the characteristic temperature for the crystalline, whereas in case of the amorphous, it is not true. Okay, what is the meaning of this point? See, if you talk about any crystalline solid, if you start melting that, so let's say suppose its melting point is 90 degrees Celsius, or we can say whatever temperature we can take, let's say suppose 200 degrees Celsius is the melting temperature. So what will happen at the 200 degrees Celsius temperature? All the crystal will get melt. Okay. Whereas if we talk about the amorphous solid, so what happens in amorphous, that there is not a specific temperature. Okay. It is actually varies, or we can say it is present over a range of temperature. So let's say suppose the melting point of amorphous solid is 80 degree. So this 80 degree is not the melting point of all the particles. Means at the 80 degrees Celsius, what will happen, that the whole solid will be simply softened over there. It won't melt. Or we can say that some part of the solid will simply get melt over there and some other part will be softened over there. Okay. So this is the difference between sharp melting point and the range of melting point, or we can say a particular range of the temperature. Okay. By sharp we are referring to its graph. Graph is only a way to represent that. Okay. Graph is simply a way to represent that. Okay. Ultimately the difference is I can say in case of the amorphous solid, a particular, let's suppose I have a particular piece of the amorphous solid. So the whole piece I can say will get melt at a range of 100 to 140 degrees Celsius. Okay. So actually I need to keep the temperature from 100 to the 140 degrees Celsius to melt all the, or we can say the whole block or whatever substance I have of the amorphous solid. Okay. Whereas in case of the crystalline solid, if I say melting point is 140 degrees Celsius, so I'll simply need 140 degrees Celsius to melt the whole crystal. Okay, this is the difference between crystalline and the amorphous. Means this is the second point number 2. I hope so it is clear to everyone. If still anyone is having any doubt, you can please ask me. Shillong, is it clear to you? Okay, wow. One is very excited. Yes. Yes. Okay, so let's move on to the point number 3. Number 3, when cut with a sharp edged tool, they split into 2 pieces and the newly generated surface are plain and smooth. And here it is not true. Okay, the newly generated surfaces are not smooth actually. Okay, they are rough. So when cut with a sharp edged tool, they split into two pieces and the newly generated surfaces are not smooth and plain. Okay. Next point, they are true solids and they are pseudo solids. Or we can say supercooled liquid. Okay. I have a question for you guys. Let's talk about the glass. Tell me, where you would like to put the glass? In the crystalline solids or in the amorphous solids? In which column you will put it and why? Why? They melt at slow rate. Any example? They have rough surface when cut. Okay. Okay, good. Your answer is absolutely correct. That glass are actually the pseudo solids. Okay. I can give you one more example, that if we observe the glasses which are present in the window panes of the ancient buildings. Ancient building means the buildings which are about 400 years old. Okay. So if we observe the glass, it is actually thick at the bottom and slightly thin at the top. Okay. Why? Just because glass is not a solid, it is a liquid. Okay. So what happened, that it is a very highly viscous liquid and its viscosity is very, very high. Okay. So its movement is so slow that we can't observe it in the few years. Okay. So we need a very huge time interval to observe that. Okay. So yes, We can say it is a pseudo-solid. Number 5. They have long range order. And they have short range order. Okay. What is the meaning of the long range and the short range? Ultimately, it represents the arrangement of the particles. Okay. Let's say suppose this is the arrangement of the crystalline particles. Okay, you can see, let's suppose these are the particles here. At these joints. So you can see there is a repeated pattern. Okay, there is a repeated pattern here, and this is so continuous. This is the meaning of the long range order. Means a repetitive pattern will be continuous. Okay. Whereas if you talk about this one, let's say suppose we have such type of pattern. Now observe this one. Here there is no regular pattern is observed. Okay, there is no regular pattern is observed here, and after the small intervals means short range order means the pattern is very small, and it will be suddenly changed whenever we move to the next section. Okay, so this is the meaning of the long range order and the short range order. This actually represents their periodic we can say repetition. Please copy and then confirm. Shillong, have you copied that? Okay. If anyone is having any doubt, you can please ask me. Next, point number 6. These are anisotropic in nature. and these are isotropic in nature. Okay, so let's understand what is the meaning of the isotropic and the anisotropic. Just look at your screen. Let's say suppose sorry, this is A type of particles and this is B type of particle. Okay, so guys, look at this. If we move in this direction, okay, I can have A type of particle or B type of particle. Okay, this is one of the arrangement. Okay, if I follow up only first line, then I'll say I'll find only the A type of particles. Whereas if I follow up only the B line, means the second line, I'll say it is only the B type of particles. But I'm saying no, I'll move like this. See, if I move like this, I'll have A and B, both type of arrangement. So actually what I'm trying to say, in such type of arrangement, if I'm moving in different directions, I'm getting the different type of particles. Okay, if I'm moving from top to bottom, either I'll find the A or B. If I move diagonally, I'll find A as well as B. Okay, so this is the different arrangement of particles in different direction. This property is known as the anisotropy. Okay, see, isotropy means in moving in any direction. When you move in any direction, I should have the same arrangement of particles. Means I should find the same type of particles in every direction. Okay, that is the meaning of the isotropy. If I find different arrangement of particles in different directions, I'll say it is anisotropic in nature. And this arrangement is just because, means we can say this arises just because of the regular arrangement of the particles. And regular arrangement of the particles we can find in case of the crystalline solids. Okay, so crystalline solids are anisotropic in nature just because they are having the regular arrangement of the particles. Okay, so please copy it. This is anisotropy. Are you clear with this one? Is there anyone who is having any doubt? Okay, good. Please copy it. What's your doubt, Tamanlong? Okay. First of all, copy it. I'll explain it to you again. Copy and then confirm. Done? Tamil long. Okay, look at this. See, they all are A type of particles. Move in any direction, from top to bottom, bottom to top, then left to right, diagonally, like this, like this. Can you say that you will get only A type of particles? Can you say that? Okay, this is isotropy. Okay, now look at this arrangement. Can you say you will find only one type of particle here? Only either A or B or AB, AB exactly in every direction. Can you say that? Okay, that's why this is anisotropic in nature. Get it now? Now is it clear to you, Tamil long? Are you still having some doubt? Okay, that's good. Okay guys, so next topic is crystal lattice. Okay. So guys, as the this crystal, okay, so it is nothing but a regular 3D arrangement of particles in the space is known as the crystal lattice. So let's write its definition first, and then we will discuss more about it. In the whole chapter we have to discuss about it. Okay, so it is the regular 3D arrangement of particles. Particles can be what? Atoms, ions, or molecules in space is known as crystal lattice. So let's check out. Look at this. You can copy that statement and yes, wait for some time. First of all, let me draw it. Okay, these are the regular arrangement, means these are the particles which are regularly arranged in the space. Okay, now the question was how these are 3D. See, as you can see, this is 2D right now. So you have to observe it. See, okay. So this arrangement of particles is known as what? Crystal lattice. And these points are what? Lattice points. Okay. Please copy and then confirm. And yes, you have to make a note of this one, that there are only 14 possible 3D lattices. And these are called previous lattices. Copy and then confirm. Done? Okay. Next, unit cell. Guys, I hope so you have seen the Rubik cube. Have you seen that? Okay, good. So let's consider the combination of the 3 by 3. Okay. So actually I can say that the bigger cube is made up of small cubes. Means the small cubes have connected, and after that connection, or we can say after that regular arrangement, it generates a bigger cube. Okay. So that smallest cube from which the whole bigger cube has been built is known as what? Unit cell. Okay. So unit cell is nothing but it is the smallest repeating unit by which we built the crystal lattice. Okay. I hope so it is clear to everyone that unit cell is nothing but the smallest repeating unit from which we can build the crystal lattice. Okay. So let's first of all write the statement of the unit cell. So you have to copy with me. It is the smallest portion of a crystal lattice which when repeated in different directions generate the entire lattice. This is a unit cell. Okay. Even you can see that the red box here, the red box is representing the unit cell. Okay. Obviously, if I start connecting these points, these lattice points, I'll get a bigger lattice. Means I'll simply get the crystal lattice. Okay. So actually, this smallest point, or we can say this smallest cube, is known as what? Unit cell. And if I start connecting these unit cells or this cube, that will generate a bigger cube. That bigger cube will be known as what? Your crystal. And yes, this smallest one will known as its unit cell. Okay. So you can please copy it, then we will continue. Done? Okay. Now look at this. Guys, look at your screen and see how we can draw the cubes. And yes, in this chapter, we have to draw lots of cubes. So this cube is actually representing the unit cell. Okay. So it can have different dimensions, like this length can be A, this can be B, and this can be your C. Okay, and yes, these lengths means these lines are connected to each other, so they must have the bond angles. Okay, like this. Let's say suppose this angle is alpha, this angle is beta, and this angle is gamma. So ultimately, a unit cell can be characterized by the two parameters. One is the edge length. Okay, see, if I make all these lengths same or different, it will generate the different geometry. Okay, and yes, along with that, if I change the bond angles, even after that I'll get a new geometry. Okay, so just making the different possible combinations, we can have total possible 14 arrangements. Okay, if I consider these 6 points, means 3 of the lengths and 3 of the bond angles. Okay, and if I change all of them, I'll tell you that how we will get the 14 different possible crystal lattices. But before that, you should have to remember one point, that a unit cell can be characterized by two parameters. One parameter is the edge length, which has 3 lengths A, B and C, which can be same or different. Okay, and yes, 3 angles between them, which can be same or different again. Okay, so this is what we have to copy here. Of unit cell. First, its dimensions. Along the 3 edges, A, B and C. These edges may or may not be mutually perpendicular. Okay, copy this first. Copy and then confirm. Done? Okay. Number 2. Angles between edges, like alpha between A and B, beta between B and C. And gamma between A and C. Okay. Thus, a unit cell has 6 parameters. A, B, C, alpha, beta and gamma. Please copy it. One second. One second, guys. Guys, kindly make it AC. This must be your AC, BC, and this is your AB actually. Okay. Copy and then confirm. Done? Guys, have you copied that? Okay. Now guys, just look at your screen. First of all, before studying the types of unit cell, we have to study about the cube. Okay. cube. One second. Just look at your screen, you have to answer me. I need one person on the system from every center. Okay. So, some basic information about the cubes. First of all, corners. Okay, how many corners a cube can have? How many corners are there in that cube? Do not draw it, or you can draw it later on. First of all, you have to answer me these simple questions. How many corners you can see here? And after the corners, you need to count the faces, and then you have to count the edges, then body diagonal, then face diagonal. Okay, very basic things. Just look at your cube, think about it, and tell me your answer. I'm giving you 2 minutes to solve this. Okay, very good, Tamalong and Shillong. What about the body diagonal and the face diagonals? Oh, hi Itanago. Good. Okay, very good guys. So just look at your screen. I guess you need some help in the body diagonal and the face diagonal. Just look at your screen first. See, these are the corners. Okay, these are the corners. Most of you has got absolutely correct answer. So you can say that there are total 8 corners. Okay, and the one wall, guys, just look at your room. I think so that is not perfectly cube, a kind of cuboidal, but just consider it as a cube. The room in which you are currently sitting, see, this imagination is really very helpful in the questions. Okay, so in the room, just count the number of walls, and these walls are nothing but the faces. So you can say there must be the 6 faces. 6. What about the edges? See, these lines are representing the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, sorry, this is not 11. This is already counted. 11 and then 12. So we have the 12 edges. Now the question is, what is the body diagonal? Guys, look at this very carefully. See, if I meet this corner with this corner, I'll say this is the one body diagonal. Guys, look at your screen. Do not copy it. Just look at your screen. Look at the body diagonal. If I passes a line, we can say, if I join 2 corners which are diagonally opposite to each other, okay, so that line which is passing through the 2 corners which are diagonally opposite to each other is actually represents the body diagonal. So the line which is with the purple dots is representing the body diagonal. Now the question is, how many body diagonals are there? How many body diagonals are there? Okay, Shillong. Okay. Guys, have you understood that what actually I was trying to say in case of the body diagonals? Shillong, what's your answer? Itanagar, think about it again. Tamelong. Okay, only two. I was saying when I join two corners which are diagonally opposite to each other, I'll have one body diagonal. And I guess so I have 8 corners. So on joining two corners, I can have one body diagonal. Then how is it possible in case of the 8 corners, I'll have only 2 body diagonals? Think about it again. Okay, good, Itanago. See? Yes, absolutely correct. There must be the 4 body diagonals. True. Okay, let's talk about the face diagonal. Guys, remember, you have to remember all these points. Okay, these are very important. Now, look at the screen. Okay, look at this. This is one face diagonal. Just pick one wall, and after picking up, just meet two opposite corners which are diagonally opposite to each other. So on the one wall, I can draw the 2 diagonals. Now my question is, how many face diagonals you can draw? Have you understood what actually I was trying to say? Yeah, very good. There must be the 12 face diagonals. Because one face can have the 2 diagonals, so 6 can have the 12. True. First of all, tell me, are you clear with body diagonal and the face diagonal? Is there anyone who is having any doubt? Shillong, Itanagar, Tamelong. This is a little bit mathematical section. Okay, good. Now, just look at your screen. Types of unit cell. First is primitive, also known as simple. Okay. Guys, you have to draw these cubes again and again. Okay. Guys, primitive means we will have the atoms. Okay. See, solid, or we can say the crystals are nothing but the regular arrangement of the particles, and we assume that particles having the spherical shape because of the atom. Okay. So ultimately what I was trying to say, that in case of the primitive or the simple unit cell, I'll have the atoms or ions or molecules, whatever it is, okay, they all are spherical in shape, but the condition is they all should be present only at the corners. like 1, 2, 3, 4, 5, 6, 7, 8. Okay. So here we can say particles are present only at the corners. Okay. Please copy it. And yes, please keep some spaces as well. Okay, because I need to write the number of atoms as well. Okay. Guys, everyone has to draw these cubes. We have to draw many. Okay. Next, number 2, non-primitive or centered. It means here atoms will be at the corners, and yes, other than the corners we can have the atoms at some other positions as well. Okay. So the first is the body center. Body center. Look at this. Here the atoms are present at the corners. Okay, and other than the corners, atom is present at the center of the unit cell as well. Okay, so here the situation is particles, or we can say atoms, are at the corners as well as at the center of unit cell. Please copy. If anyone is having any doubt, you can please ask me. Okay, let's move on. Next, face centered. See, atoms are present at the corners as well as the faces. So I know we have 6 faces. So look at this. 2, 3, 4, and then 5, 6. Okay. So what can I say? Particles are at corners as well as on the faces. Please copy. And yes guys, please keep some space as well. I'm repeating, we need to write the effective number of atoms as well. Okay. Confirm once after copying that. End centered. In the end centered, we have the atoms at the corners as well as at any two opposite faces. Okay, so we can have only 3 possible combinations for the any two opposite faces. Okay, you can choose any one, whether it is front back, top bottom, or left or right. Okay, like I am picking up the top and bottom section. Okay, so I will say atoms will be present, or we can say the particles are at the corners as well as on the, or we can say at any two opposite faces, at any two opposite faces. Copy. Next, edge centered. Here, the atoms are at the corners as well as on the edges. Look at this. Please copy it. Atoms particles are at the corners as well as on the edges. Copy and then confirm. Okay. Done? Okay, good. effective number of atoms in a unit cell. This is represented by the Z. Okay. Guys, please do one thing. Just look at your screen. I need one person on the system. Need not to write anything. We have to understand this. Okay. And with the concern of all, I need answers from you. Okay. And try to imagine the things. Okay. So first of all, consider one thing. And yes, please be in the room. Try to imagine. Okay. The room in which you are sitting right now. That room is cube in nature, means that is exactly a cube. Okay. And my question is, if I am using a sphere, okay, and I have to fit that sphere in that cube, is it possible that I can completely fit that sphere into that room? Is it possible? Can I fit that sphere in that room? If it is cube, okay, no. Yes, Shillong, we can do this. See, cube is a regular geometry. Okay, so every length is equal and every bond angle is 90 degree. Okay, so if you use a sphere, see the room in which you are right now you are sitting, now that is not a cube actually. Okay, that is actually a cuboid. Okay, so just try to consider a cube. Okay, and try to put a ball into it. Okay, of the equal dimension, and what will happen, that every face of the cube will be touched by the ball. Okay, and that ball is nothing but what? Atom. Okay, if they are having the similar size, I can say the diameter of the sphere should be equals to what? Edge length, means one length of the cube. If that is true, then definitely I can say that will be fit into that cube. Now, are you clear with this one? Okay, Shillong and Itanagar. Guys, now are you clear with this one? That I have to put a ball into a cube, and yes, it is possible. My question is, in this current situation, where will be the center of sphere? Can I say the center of sphere and the center of the cube should be at the same point? Can I say that? The center of the sphere and the center of the cube should be at the same point. Some guys are just looking at me that the person in front of us is trying to say something, don't know what. Okay. Okay. See, I was just trying to say, I was just asking that the center of the sphere and the center of the cube, okay, whether will it be at the same position or not? Yes, definitely it will be, okay, because we have the same dimension, as in the edge length of the cube was exactly equal to what? Edge length, or not edge length, a diameter of the sphere. Okay, so if that is true, then definitely I can say that yes, the center of the cube and the center of the sphere will be at the same point. Okay, so in this current situation, if I ask you, how many spheres is exactly inside the cube? How many spheres? I know this is a very ridiculous kind of question, but yes, you have to answer. Oh yes, Tamalong has given the correct answer. In this current situation, how many spheres are inside the cube? What happened, Shillong? Itanagar? Yes, obviously there will be of one sphere. Means inside the one cube there is only the one sphere. Okay. Now I am saying one thing. Imagine you are pushing that sphere, okay, and what you have to do? You have to push that sphere, and yes, make sure you have to shift the center of sphere on one of the wall of the cube. Okay, move it in any direction, okay, but you have to do one thing, that you have to shift the center of sphere on one of its walls, or we can say one of its faces. Now my question is, when the center of sphere will be at the face or on the wall, what section of sphere will be inside the cube? Are you clear with my question? When your center of sphere will be on the wall, how much part of the sphere will be inside the unit cell? Is exactly half. Okay. So in the current situation, the center of the sphere is on the face, and this situation is known as the face center. First case, where center was exactly lying inside the unit cell, that was known as what? Body center. Now center is shifted to the face, it will be known as what? Face center. Got it? And yes, your answer is absolutely correct. If I say the face center, it means that half of the sphere will be inside the unit cell or the cube, and half part will be outside. Now my next question, shift the center on the edge, at any edge. From the face, see, we have now shifted to the face. From the face, you have to shift that sphere in such a manner that now the center of the sphere should lie at the edge. Now in this current situation, how much part of the sphere will be inside the unit cell? How much part? Okay, very good. And those who are talking in the class, the last benchers in the Shillong Center. Yes, I am talking to you. Hi. Okay. I hope so. You won't do any mistake in the questions. Okay, I hope so. It is clear to everyone that when center will be shifted to the edge, 1/4 part will be inside the unit cell and 3/4 will be outside the unit cell. And this current situation is known as what? Edge center. Okay. This current situation is known as what? Edge center. Do one thing. Now, shift the center of the sphere on the corner, at any of the corner, from the edge center to the corner. So, when you shift the sphere, means the center of the sphere on the corner, now how much part will remain inside the unit cell? Okay, good, Taman Long. What about you, Itanagar and Shillong? Now I'm saying from the edge center to simply shift it to the corner. So Shillong, does it mean that there is no difference between corner position and the edge position? Is it? Yes, absolutely correct this time. Okay. So guys, now look at your screen. I'm just revising it. Look at your screen. If I say body center, actually there will be only one atom inside the unit cell or the cube. If I say face center, contribution will be the half. If I say edge center, contribution will be 1/4, and if I say corners, contribution will be what? 1/8. Clear? Is it clear to everyone? Okay. Please copy it. Ultimately, you have to remember it that body center means 1, face center means contribution half, edge center means contribution 1/4, and corners means 1/8. Okay, that's what you have to remember. Done? Okay guys, now look at this. Look at this diagram. In the types of the unit cell, first was the simple or the primitive. Now, actually, we were representing one sphere at one corner. But now we have just learned that corner means the total sphere won't be inside the unit cell. Only 1/8 part will be inside the unit cell. Okay. If I would like to calculate the Z for it, which is effective number of atoms, means exactly how many spheres can be inside the unit cell, I can say from one corner I'll have the 1/8 part, and like this I have total 8 corners. I have total 8 corners. Okay. So I'll say 1/8 into 8. So it is the 1. So in case of the simple or primitive unit cell, effective number of atoms will be exactly 1. Are you clear with this one? Okay, very good. Now it's your chance. Determine effective number of atoms in the body center, edge center, face centered, and so on. Please calculate the number of atoms, then we will discuss about it. Be careful while solving the questions. Please refer the diagrams. Just get back to these diagrams again and then calculate it. Shillong, I haven't got the answers. Itanagar. Wow. In the fractions we are getting the answer. Have you understood how I was solving it? See, in the body center, one atom is exactly inside the unit cell, so contribution will be 1. From the corners, I'll have the 1 by 8 into 8, so the total atoms would be the 2. In case of the body center, I'll have the 2 effective number of atoms. Then, in case of the face centered, 1 by 8 into 8 plus 1 by 2 into 6. Because one face can contribute only half and there are total 6 faces, that's why I'll say it is 1 plus 3, which is nothing but the 4. End centered, 1 by 8 into 8 plus 1 by 2 into 2, because the atoms are present only at the 2 faces, that's why I'll take only 2. So this is 1 plus 1, which is 2. In case of the edge centered, this is 1 by 8 into 8 plus 1 by 4 into 12. So this is also 4. How many of you has got the correct answer? Raise your hand. In the Shillong Center and Itanagar and Tamalong, you have to use the chat screen. Only 1, 2. Oh wow. Only 2 students are there. And rest are busy with their talks, like TikTok. Guys, have you understood this? Is there anyone who is having any doubt? Okay, good. So, I can conclude one thing. Simple cubic has got one atom. Body centered cubic, which is the BCC, 2. Face centered cubic, 4. Edge centered cubic, 4. End centered cubic, 2. That's what you have to remember. Please copy it. Done? Please copy and then confirm. Okay, so let's move on. Determination of formula of compound. Guys, just look at your screen. First of all, understand the concept, and after that, I'll give you a few questions to practice. Question number 1. Determine, or we can say, a compound is formed by two elements P and Q. P occupies all the corners and Q is present at the faces. What will be formula of compound? Okay. So please stop writing it. Okay. Do not write the question. Just look at your screen. First of all, understand the concept. We are having the two atoms P and Q. Okay. So it is saying P are present at the corners. So you have to just consider the corners, and yes, corners, at the corners we have the contribution of 1 by 8. So we can have total 8 corners. So I'll say 1 by 8 into 8. And now it is saying Q is present at the faces. So obviously at all the faces, one face has the contribution of half. So 6 will have what? 1 by 2 into 6. So it is 1 and it is 3. So it is nothing but their respective atoms. Okay. So formula will be what? PQ3. Please copy. Clear? Confirm once. Are you clear with question number 1? Okay, good. Please copy it. Yes, PQ3. Now the next question. I'm not writing the whole language. I'm just saying that A are at the corners, B at body center, C edges. What should be the formula of the compound? So just look at your screen. After that, I'll give you question to solve. A, B, C. Okay. So A is at the corners, so it should be 1 by 8 into 8. Body center means directly 1, and edges means 1 by 4 into 12. Simply solve it. You will have 1, 1, 3. So formula will be A, B, C3. Easy? Oh, very good. Tamilong and Shillong. So next question will be for you. Done? Next question. A is present at half of the corners. Means A is present at half corners. Half of the corners, all the faces, and C is at body center. Determine the formula of the compound. Tell me the answer. What should be the formula for this question? Oh, yes. Please do not keep it in the fractions. Solve the fraction as well. Atom should be the whole in the whole numbers, like 1, 2, 3, 4, 10, 20, 100, 1000, whatever it is. Don't keep it like 2 by 3, 1 by 2, 5 by 2, 7 by 8, something like that. Okay, Shillong is given. Again, I'm saying do not keep it in the fraction. Please solve the fraction. Okay, let me tell you. A, B, C. First of all, corners, it is saying the corners, so just keep it 1 by 8. Saying half of the corners, so we can have the 8 corners, so half of the 8 is nothing but the 4. All the faces, so it should be 1 by 2 into 6. Body center is simply 1. So it should be 1 by 2, 3 and 1. Now, how to solve this fraction? See, simply pick the number which is present in the denominator, okay, and multiply with that number in the whole equation. So I'll say I'll multiply it with the 2. This is 2 and this is also 2. Obviously, this 2 and 2 will get cancelled out. So it will become a whole number. So this is 1, this is 6 and this is 2. So answer will be what? A, B6, C2. Clear? Are you clear with this one? Now next question is for you. Good. Please copy and then confirm. Four. Corners only at 3 faces. C. Edges. Solve. Okay. Let's see. A, B, C. So corners means all corners. Faces is half. It is saying only 3 faces, so out of 6 I'll have the 3. Edges means all the edges, so this should be the situation. 1, 3 by 2, 3. So obviously I need to convert it, so I'll simply multiply it with the 2, because in the denominator maximum number is 2, that can make it as a whole number. So on solving, I'll have 2, 3, 6. Answer will be A2, B3, C6. Very good. So guys, this is the level 1 in such type of problems. Okay, so we have 3 levels, 2 and 3. Okay, so in the next class, we will first of all discuss the level number 2 and then level number 3, and after that we will continue. Okay, so I hope so up to this one everything is clear to everyone. Please revise it again, and yes, thank you so much. I'll see you next time. Till then, take care. Bye bye.